Okay, this is a continuation of lesson 8.3. We're now on the shell method. So if you turn to your flip book, it should be the page that's labeled shell, second to the last. And if you open it up, this should be, well, technically your page 8 and page 9. You will know it's shell because on the top it says cylindrical shells, all right? So this is the other method of finding volume when your area is being revolved around an axis, okay? Okay, so why do we need cylindrical shells? So this is a little bit harder to explain. So again, open mind, all right? So washer, we can picture having these discs stacked up. So why do we need this cylindrical shells? So what this is saying is typically a cylinder, right? A cylinder, a three-dimensional cylinder looks something like this. When you open it up, you have a circle on top and a rectangle on the bottom and a circle on the bottom. So what you were really using is this piece right here. These are cylindrical shells because it's only around the outside. We don't care about these bases, top and bottom. No, we don't care about that, right? So first of all, how are these rectangles calculated? Well, this rectangle needs to wrap around the circle. So hence this part is the circumference, 2 pi r, and the height here is whatever height it is. So the area of this rectangle will be 2 pi r times height, right? So this is a shell of a cylinder, the outside of a cylinder. Or if you recall in geometry, it's the lateral height, lateral area of the cylinder. So around the outside, like a soda can, just the outside, not the top or the bottom, okay? All right, so why do we need this? Sometimes our circle, our area being revolved around, the height is changing, right? So a very good typical example is something like this, where you have this linear function and a quadratic function being spun around, right? So it's being spun around. One of my students said this looks like a dreidel. So again, whatever helps you see this picture, but this is the picture is being spun around. If I were to use washer, you will see that the top of the circles is limited by the linear function, but then the bottom circles are now limited by the quadratic. So if I were to use washer, which is absolutely doable, I will then have to cut this in half and integrate it from the top to where it breaks off from the linear to the quadratic, and then take a second integral from that point to the bottom of the quadratic. So essentially you need to take two integrals to figure out this volume, which is a lot of work. So then mathematician says, hey, there must be another way to figure this out that's a little bit different, maybe a little bit quicker. So if I were to use these shells, so imagine using like a really, really thin straw, like a stirrer for your coffee. So I use a really, really thin straw and I go like this. I try to match the height on top and bottom, right? And then next I use a regular straw, you know, the ones like you get at McDonald's, a regular straw. So I'm gonna use that, right? And then the next layer, I'm gonna use a boba straw. I'm gonna do that. And again, I'm using these cylinders to just go out, and notice how each of my cylinders is gonna be capped at this height and this height. The height is gonna be restricted, and it's gonna go out and expand out until I get to this really tiny edge on the outside, which is gonna be a really, really, really fat cylinder, like almost like a masking tape, So masking tape roll, right? A tape roll that's really, really small and really wide, right? So again, that's the idea of these shells. You just kind of build these rectangles around. So these are called cylindrical shells. Now calling a cylindrical shell is good. It's just a lot of words. So that's why we just kind of shorten it to shell method, right? So you now have the washer and you have the shell method. Okay, same as always, you really want to make sure you draw this on a graph paper, because if you don't, it's going to be kind of a pain, right? So I'm going to use my graph paper like I've been, right? All right, get rid of all my stuff here. All right, so I copied that so I can know what function we're dealing with. Okay, so game plan, like always. I always have a game plan to figure out what kind of a area I need to draw this. So I have y equals square root of x right here. X equals 4 is right here. And y equals 0. Okay, so it's this piece right here. And I'm going to revolve it now around the y-axis. So it's going to look something like that. Okay, so that tells me a lot. It tells me I need a lot of room in quadrant 1 and quadrant 4. I don't need quadrants 2 or 3. Okay, perfect. All right, so now I'm going to draw this. All right, 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, probably don't need that much. Okay, so now I'm going to draw my function. My function is y equals x, root x. So I have 0, 0, 1, 1. 4, 2, so that is my square root function. X equals 4 is right here. y equals 0 is right here. This is my original piece, right? And again, I always suggest that you kind of highlight the original piece so you kind of remember where your integration is, okay? All right, my axis of revolution is about the y-axis. So my y-axis is right here. I'm going to spin this way. And then I am going to go ahead and draw the mirror image so I can sort of see what is happening here. So here is my picture. Right. So this actually is almost exactly like the first example I gave you when we first started doing volume. When I said, oh, when you go to the mall and you put the coin in, it goes around and around and around. This is actually the thing that has that is the container that lets you put the coin in, right? Because remember that container outside looks like a cylinder, and on the inside it curves in like that, right? So this is exactly that mechanism, okay? All right, so I'm going to go ahead and cut this out and glue it down on my notes. Okay, all right, going to my notes. Okay, so what does a typical piece of shell look like? A typical piece of shell looks something like this, where your height, zoom in a bit so you can see more, where your height is being restricted by the function. So here's your height, right? And it's going to go out this way. Here's your height. Oh, oops, not very good. Sorry about that. Let me try again. So here is what I picked. And so mirror image wise is going to be on this side. This is the piece of cylindrical shell that I picked to look at. Right? So what is the radius of the shell? Well, the radius is whatever value I chose to stop here at the x value. So then the radius of the shell, radius, is just x. This is the one thing that won't show up on your function. So you kind of have to know this. The radius is this variable x, right? And then the height of your function, the height of your cylinder, the height is trapped between here and here. And this is where my top and bottom shows up. So the height would be top minus bottom, where the top function is x equals 4, right? And then, sorry, not x equals 4, apologies. The top function is root x, square root of x, minus the bottom function of 0, right? What about the 4? The 4 will play a role in a minute. Every piece of information given to you will play a role, right? So let's clean this up. This is root x, okay? And then the volume of this is to add up infinitely many of these shells. So the shells are these rectangles, which a formula says 2 pi RH. So 2 pi is our coefficient. We pull it outside. And we have our radius times the height. The radius was x from here, and the height was root x. And this is a dx problem. Hence, you know then my integral goes from 0 to 4, 0 to 4. Hey, where did that 4 come from? That's that piece of information given to you, okay? So cylindrical shells grow the opposite way of washers. Washers stack perpendicularly to your axis of revolution. Shells will grow or expand parallel to your axis of revolution. So if my axis of revolution is vertical like this, my shells are going to expand parallel to it. And so again, notice it's growing side to side. Therefore, this is a dx problem. Okay. So vice versa. If you have a horizontal axis of revolution to be parallel to the horizontal, you will stack up and down. Therefore, it's a dy problem. Lastly, before I move on to the problem, notice down here I gave you a little hint. If you're rotating about the y-axis, the radius is x. This is kind of reminding you that, hey, that y-axis doesn't really say that, but it's something you need to know. So kind of remember this, that, hey, your radius is x, and then your height is top minus the bottom function, all right? So shell method is a little bit easier in terms of working it out. It's a setup that's a little bit complicated because you got to think about, oh, top minus bottom, right minus left. But once you have that, the work itself is not bad. You can combine these x times root x. So this is x to the 1, x to the 1/2. Combine it x to 3/2 dx, right? Take the antiderivative, x to the 5/2, and then multiply by the reciprocal. So you get 2 pi evaluated 2/5, and then 4 is really 2 squared, the 5/2. You don't need to subtract 0 because we know we get 0 that way. So I can combine these and say this is 4 pi over 5. I can even go as far as this. 2's will reduce out. 2 to the 5th is 32. So I get 128 pi over 5 as my volume. Okay. All right, next problem, moving on. I have this function here. I am going to go ahead and find my graph paper so I can graph this out. Erase all my stuff from before. Okay, so again, game plan. This is y cubed equals 3. So y cubed equals x, so y equals cube root of x. Again, game plan for myself, cube root of x looks something like this. And then y equals 2 will look something like this. X equals 0 looks something like this. So this is the piece I'm looking at. I'm going to spin it about the x-axis. Okay, so spin it this way. So that means I'm going to have something that looks like that, right? Okay, so again, this gives me the information that I need quadrants 1 and 4. I don't need quadrants. Oh, this is 1 and 4. Sorry, I was wrong in the previous problem. It was quadrants 1 and 2. So this is quadrants 1 and 4 that I need. Okay, all right, so let's see. We need quadrants 1 and 4. Let's dip this down. Go all the way across this way. 1, 2, 3, 4, 5. I think I do need that much this time. Okay, so y cubed equals x. That's really y equals cube root of x. Cube root is 0, 0, 1, 1, 8, 2. So it's really, really wide this way. So 8, 2 all the way out here. Okay, y equals 2. So y equals 2 is this horizontal line up here. And x equals 0 is this vertical line here. So this is the piece I am dealing with. All right. And then my axis of revolution is the x-axis. So here is my axis of revolution. It's going to spin around this way. And then lastly, to show you the three-dimensional picture, which is really, really kind of cool in this case. So I'm going to go ahead and show you this piece here and connect my vertices. All right, so this is the piece. Now, if you look at it sideways, this is actually kind of like those long shot glasses. So I don't have a better example here, but you know, the long shot glasses that look like this is long and cylindrical, but the inside only contains this much, right? So this is exactly the shape that we're dealing with here, all right? Okay, so with that said, I am going to, for me personally, put a little bit of shading in because I like that, but it's really optional. All right, but don't forget your key point is to cut this out and glue this down. All right, so I'm gonna cut this out, cut, and glue it down on my paper. So you can see for me, even for me, this is big, but I have the advantage of zooming in. So you might want to redraw or shrink down your scale so that you can actually fit this, okay? All right, again, if you want to see, I always like to show it, but if you want to see a typical shell piece would be something like this, where you go down and you go across. This is a typical cylindrical shell piece, right? So you see, first of all, that your radius is whatever y value I chose to. So this is your radius, right? So your radius is a y value, okay? And then your height, the height of your function, well, it's trapped between this and this. This is your right, this is your left. Your right function is the y cubed function, so right minus left, that's your y cubed function. Your left function is 0. That is the vertical line there. So y cubed minus 0, which makes it y cubed. All right. So then you can see, lastly, because this is a horizontal axis of revolution, to be parallel to it, my shell is going to go up and down. It's going to increase up and down. So this is a dy problem. So the volume of this is 2 pi r h dy. My radius was y. My height was y cubed. And since this is dy, the interval is 0 to 2 based on the original blue piece that I have highlighted there. Okay, the rest is straightforward. You clean up by making this y to the 4th, dy, 2 pi, evaluated y to the 5th over 5, 0 to 2. So 2 pi times 32 over 5 minus 0, you don't need the 0. So my final answer is 64 pi over 5. Again, I believe that shell is a little bit easier to calculate. I mean, at least the work you have involved. It's a setup that is a little bit more work, okay? All right, next problem. Next problem is one of my favorite ones, and I'm sure you're like, oh, great, that's not a good sign, but it's okay. What I like is not necessarily what everybody likes, okay? So the next problem looks something like this. You have y equals x squared, y equals 4, and you're splitting this about x equals -4. This is a wider problem. It's going to take about quadrants 1 and 2, okay? So again, game plan, I know that I have y equals x squared like this, y equals 4 like this, x equals -4 is on this side, so I'm gonna have to spin it this way, right? So it's gonna take up a lot of space, okay? All right, so good game plan. Let's see what this looks like. I purposely didn't finish it because I wanna show you more on this side. So I'm gonna have a longer x-axis. Don't need much of the y. Oh, I do, sorry. I need enough to go up, okay. So 1, 2, 3, 4, 5, -5, 1, 2, 3, 4, 5. And that part is unnecessary. Okay, y equals x squared. So 0, 0, 1, 1, 2, 4, and this is my parabola. Then you have y equals 4, right? So this is really the piece I'm looking for. This is the piece I'm working with. And then your axis of revolution is going to be x equals -4. So x equals -4. Oops. X equals -4 is right here. It's my axis of revolution. And then last but not least, I'm going to show my mirror image. Oh, I don't have enough space. I didn't draw enough, but that's okay. This is just a mirror image, so not a big deal. So this is my mirror image. And so if you connect the vertices, you have this, you have this. Oopsies, you have this here, and you have this piece right here. It's a bundt cake. It's upside down bundt cake, but the bundt cake has a bigger hole in this one. Or it's a bagel. Some students say it's bagel, the bottom half of the bagel, right? Or bottom half of a donut if the donut's not very circular. So yeah. I like this one because there's a lot of examples to use to kind of understand what the shape really is. Okay, but of course, as always, make sure you cut and paste this down. Right, I'm gonna put this into my notes. Okay, again, this one's big, so you might want to shrink it down, right, by changing your scale, or you can do whatever you feel like will give you a better picture, okay? All right, so I'm going to show you a typical piece of shell, right? So a typical shell piece is going to be something like this, where you take this and mirror image it, and then come down, and come down this way. Oh, that last one is, okay. All right, so something like that. So this time your axis of revolution moves. So this is where you are really being demanded to memorize your right minus left, top minus bottom. Whenever your axis of revolution moves in a shell problem, your height and radius, one of them will be top minus bottom, one of them will be right minus left. So if you take a quick look, it's a little bit hard to understand, I agree, but once you walk it through, it shouldn't be that bad. It says if you're rotating it about a line that is x equals a number, not the axis, but x equals a number, then you're going to treat the axis as a variable x, and your radius is going to be right minus left, and your height is going to be top minus bottom. So first thing I'm going to do is I'm going to remind myself that radius is going to be right minus left, and my height is top minus bottom. Okay, so then what do? Okay, so I'm following the direction. Direction says treat my original x-axis or y-axis as a variable x, and then here is my rotating axis that is a -4, so it will be right minus left. My radius will be x plus 4, right? Because again, I'm going to try to explain this, because your radius is really your whatever x value you choose, right? But you got to include the fact that the radius goes all the way out to here. So if you choose a radius that's on this side, that piece right there, right? The radius of that shell is whatever my x value here is plus the 4 here. So you need all that space. So that's why you need to add the 4, which is minus a negative 4, okay? Then if you are looking at your height, the height of my shell is going to be trapped between this top function and this bottom function. So the top function is y equals 4. The bottom function is x squared. So there you go. There's my top and bottom. So the volume of this is 2 pi integral my height, 4 minus x squared, times my radius, x plus 4. If you swap it around, doesn't matter. Sorry, I swapped it around. H times r dx. And then the dx goes from negative 2 to 2 because that is my negative 2 to 2 interval. You cannot double these because it's a different thing. Shell, you don't double. You just kind of keep it as is. All right. All right. Clean this up. Multiply this out. I'm going to distribute. I'm distributing the 4. So 4x plus 16 minus x cubed minus 4x squared. This time I have no common terms to combine, so I'm going to go ahead and work this out. When I work it out, I like standard form, so I'm going to work this out from the highest power down. All right, and work this out and go negative x to the 4th over 4 minus 4x cubed over 3 plus 2x squared plus 16x. Evaluate negative 2 to 2. Okay, so 2 pi 2 to the negative 2 to the 4th is negative 16 over 4 minus 4 times 8 is 32 over 3. 2 times 4 is 8, and then 32 minus, plug in negative 2, still get negative 16 over 4. This time I'll get plus 32 over 3, and then I still will get a plus 8, and I'll get a minus 32. All right, so some of these actually will nicely cancel out. So let's see. I have a negative 16 over 4 minus a negative 16 over 4, so that's gone. I have an 8 minus an 8, so that's gone. So what I have left over is actually nice and easy, or at least straightforward. I have negative 64 over 3, combining those two, plus 64. So I get 2 pi negative 64 plus 192 over 3. So my answer is 2 pi times 128 over 3. So I get 256 pi over 3 as my final answer for my volume. Okay. Fun answers, I know. Okay, last one. Last one on the show. So I have this one. I'm going to go to my awesome graph paper once again. Graph paper is very essential. If you don't have graph paper, it's really, really, really almost impossible to figure out what the graph looks like, right? Okay, y squared equals x. My game plan, y squared equals x is a sideways parabola. This way it's positive. This one will be changed into y equals negative x plus 2. So it'll be plus 2 and down, so something like that. And I'm going to spin it around y equals 3, so somewhere up here. Okay, so that means I need some space up top. All right, so that means then I have a lot more quadrants, quadrant 1, and maybe a little bit of quadrant 4. All right, so not much in the other quadrants. Okay, so I'm going to have my awesome quadrant 1 and something down here. 1, 2, 3, 4, 5. Okay, just to kind of know my scale. All right. Y squared equals x. Based on my game plan there, it looks like I need 0, 0. I need 1, 1, 1, 1, and 2, 4. That's what it looks like so far. So I'm going to put my parabola in. Okay. And then my equation, y equals negative x plus 2. So at positive 2, positive, I went down 1, right 1, down 1, right 1, down 1, right 1. Perfect. I know then that will close that up. This is the piece I am dealing with very nicely. Okay. And then my axis of revolution is at y equals 3. So here's my y equals 3 axis of revolution. Spin around. Then lastly, my mirror image to allow me to see the picture. So this and this and this. So my mirror image is looking like that and that. So once again, if you turn your head sideways, you should be able to see this is that insulated bowl that we were dealing with a couple problems ago. So it's very, very similar. It's just maybe a little bit bigger in terms of its volume. Okay. All right, so go ahead and cut this out and stick it into our notes. All right, This one may be a little bit easier to see the cylindrical shell, but again, you have to keep an open mind and kind of try to picture this, right? So a typical shell would be something like this. And I go all the way out. Oops, no, not that way. All the way out. Here's my shell, and this is one of my pieces. Oh, my mirror image is not, well, I didn't do a very good job. Let me try it again. All right, so typically I do that, and then so my other end is here. Okay, yeah, this is better. I should really just find this mirror image before I do the shell piece. So my shell piece is somewhere like that, okay? Not the best picture, but I try my best. Okay, so as what we said before, when your axis of revolution moves, then there's more involved here. So it does give you a little hint here. It says, if you're rotating about a line, y equals a number, then you're going to treat the x-axis as a variable y, and your radius is top minus bottom. Your height is going to be right minus left, exactly opposite of the other one, right? So your radius is top minus bottom, right? So what is top? Well, top is my axis of revolution, because my axis of revolution is y equals 3, and this is my variable y here, right? So the top will be 3 minus y, or radius is going to be 3 minus y for your top minus bottom. Your height is going to be right minus left. So if you look at your original piece here, your right function is this one right here. That's your right function, because if you're coming from this way, that's your right, and you're going to hit this second, that's your left. So your right is your linear, your left is your quadratic. Your linear, if you write it correctly, will be x equals 2 minus y. So then your height is going to be the right of 2 minus y minus your left, y squared. Okay, so the volume of this is 2 pi again, and then your radius times height. So radius times height, dy, and then because it's a dy, your interval is going to go from -2 to 1. So -2 to 1 up here. Okay, so this one is so far the only one that requires a little bit more work. You have to multiply this out. So I would recommend just kind of distribute the 3 and the -y. Right? If you distribute, you get 6 minus 3y minus 3y squared. And now distribute the -y, so -2y plus y squared plus y cubed dy. Combine like terms. You don't want this many terms, so y cubed, and I have minus 3y squared and 2y squared, so minus 2y squared minus 5y plus 6 dy. Okay. All right. So then go ahead and take the antiderivative. I have y to the 4th over 4 minus 2y cubed over 3 minus 5y squared over 2 plus 6y, evaluate -2 to 1. All right. So I get 2 pi, plugging in 1. So 1/4 minus 2/3 minus 5 over 2 plus 6. This one's nice and straightforward. Plug in a -2, I get positive 16. Oops. Positive 16 over 4. And then -2 cubed times -2 is plus 16 over 3. And then -2 squared times 5 is -20 over 2. And then minus 12. So you get 2 pi. 1/4 minus 16 over 4th is -15 over 4. -2/3 minus 16 over 3rd is -18 over 3. -5 halves minus a -20 halves, so positive 15 over 2. And then 6 minus a -12, so plus 18. All right, that gives me 2 pi. And since these are over 2 and over 4, I can combine those. So -15 over 4 plus 30 over 4. And then this is -6 plus 18, so plus 12. So I get 2 pi, and I get 15 over 4 plus 12. So 2 pi, 15 plus 48 over 4. So that gives me 2 pi times 63 over 4. You can reduce these two down. So you get 63 pi over 2 as your final volume for this problem. Okay? All right, really spend some time, especially really spend some time to remember. I hate saying memorize, but remember this and this, because that is really important for you. These are both applicable, even if my axis didn't move and they stayed on the y or x axis, then it would just be -0, right? So you will still have your variable x and y as your radius, okay? All right, guys, that's it.